Hi everyone, my name is Zhang Yuxin, and the title of my presentation is Optimization Cooling System of PV Thermal Collector System for Sustainable Green Technology. For this presentation, I will cover the background and importance of the cooling system and the methodology we use to implement the cooling system, and the result and conclusion we derived from the experiment. Now let's get started. The PV technology is very important for the solar energy utilization. It converts the solar into electrical energy we use. The major challenge with the PV panel is that the efficiency decreases as the temperature increases. We know that for every 1 degree Celsius increase in the panel, the efficiency can drop at around 0.25% to 0.5%. This makes the cooling technology is very important for maintaining the optimal performance. There are two main types of the cooling method, that is passive cooling and active cooling. For the passive cooling, it relies on the natural convection or conduction. It often uses materials like the copper or aluminum to transfer heat away from the panel. The other is the active cooling. It normally uses external devices like the pumps or fans to manage the heat more aggressively. So in this our study, we implemented a hybrid cooling system that combined both the air and the water cooling. This approach offers greater adaptability to the different environmental conditions. By applying the strengths of both the air and the water cooling, the system is able to improve the electrical output and enhance the overall efficiency for the PV panels compared to the traditional cooling method. The methodology is mainly based on this flowchart here. So the hybrid cooling system we developed, it combines both the air and water cooled technologies to manage the heat efficiently. Actually, it is a low-cost solution that can be easily stored on existing solar panel setup to make it both practical and scalable. For air cooling mechanism, the air cooling component uses fans that can automatically turn on when the panel temperature exceeds 35 degrees Celsius. For higher temperature, the water cooling system comes to play. Water circulates in a closed-loop system, and the pump is triggered when the panel temperature reaches 45 degrees Celsius. The water absorbs heat directly from the panel surface to enhance the cooling effect. For control and monitoring, an Arduino Uno microcontroller to manage the entire system. It receives temperature data from DS80B20 sensor. It attached to a PV panel that can use the information to automatically switch between the air and the water cooling as needed. This ensures that the panel can remain within optimal temperature ranges to maximize the performance without excess energy uses. So our experiments were performed at Xiamen University, Malaysia. These two figures show the front view and the back view for the setup for our cooling mechanism. We used 10-watt solar panel positioned at a 30-degree angle, facing the sun to optimize sunlight capture. The air cooling system consists of aluminum heat sinks and fans installed at the back of the panel. The heat sinks help dissipate heat, while the fans to ensure effective airflow across the surface. Silicone thermal pads were placed between the panel and the heat sinks to improve the thermal conductivity to ensure better heat transfer from a panel to a cooling system. The water cooling system circulates water across the front surface of the PV panel. The water is collected through an open drain then flows back to the tank for continuous circulation. So this closed loop system to ensure the effective cooling without the wasting the water. The Arduino control unit is the central for the whole system. It can help to manage the entire cooling process to ensure the system operates efficiently. So in our experiment, we test the hybrid cooling mechanism outdoors on sunny days in May 2024 from 8 a.m. to 5 p.m. The measurements were taken for every 30 minutes. As shown in this two figure, the water pump activates between 10 a.m. and 4 p.m. For temperature analysis, the cold panel temperature always remains at an average of 33 degrees Celsius throughout the day. It remains a stable and a lower surface temperature for the solar panel. Moving on to the effect on voltage and current output, especially after 9:30 a.m., we saw a clear increase in both the voltage and current for the PV panel with the cooling mechanism. This shows that how the cooling system can help to maintain optimal cell performance to minimize the voltage draws that can typically caused by the overheating. Finally, let's talk about the impact on the power output, especially between 12 p.m. and 1 p.m. The highest output power approaches the rated power, which is 10 watt. For efficiency improvement, the efficiency of the solar panel is critical indicator for the ability to convert the sunlight into electrical energy. Mathematically, the electrical efficiency is defined as the ratio of the maximum power output P max to the product of the solar irradiation G and the surface area for the PV panel, as given in the equation here. So with our calculation, the efficiency of the PV panel is increased from 16% with the PV system to 20% within the cold PV panel. Let's highlight that the designed cooling system it can improve the power conversion effectively. This is our advantage for the designed cooling mechanism. The first is the implementation of the microcontroller-based cooling system. Compared to the continuous operating cooling system studied by the previous research, our system operates only when necessary to cool the solar panel. To use the least amount of the water energy, this target approach not only reduces unnecessary energy wasted, but also extend the overall lifespan for the whole system. And the other is combined with the passive and active cooling method. So in our study, we not only shows a significant development compared to the previous research as this in this table. Finally, let's have a conclusion. We successfully developed the hybrid cooling system with air and water cooling, and the data clearly show its effectiveness. For the improvement for the PV output, the system reduced the temperature at the average of 40 degrees Celsius. The voltage, the current, the output power are all getting increased in the power generation during the peak sun hours. The electrical efficiency for the PV panel with the cold system increased from 60% to 20%, representing a 28% improvement. Overall, the hybrid cooling system realized efficient temperature management and had a direct and positive impact on both the electrical output and efficiency. It proves that the effective cooling can play an important role in developing the performance of the solar panels, particularly in some regions with the higher solar irradiations. That's all for my presentation. Thank you for all your listening.